thank you very much for coming. Would you please do what you're going to do?
All right, thank you. Tonight's presentation stems from Ron putting the hard word on me to finish the 6-metre field day amplifier. We've been working on various amps for some time, and the 70 centimetre amp is one that we worked on previously. This is a recipe I've used on about 20 amplifiers now, right up to 23 centimetre 600 watt WPQL RF decks. So I published it on various Facebook sites, and I have a Dropbox site where you can go and get further information if you want. This is the front panel of the unit, as you can see from it in front of you. I like to see a voltmeter on the front, but when Ron did it, he elected to put only an ammeter. It is a bit superfluous because with regulated supplies it's usually there or not there. And the characteristic of the amps I've done are the dual needle SWR, because that's important. It allows you to set the drive level. It allows you to see what the SWR, and it's also useful for setting up the radio. Back panel pretty straightforward. Ron elected to use a 6-inch fan, which I immediately cooked for him while I was setting up the 24 volt supply, but it has worked out to be a good option. The fan is, while it won't push a big load, big pressure load, it has a high flow rate, and with the little director here, it pushes most of the air underneath, where some air can go down over the top and keep the top components cool. This is a Larcan board, but it's two parts. It never was delivered to us as a Larcan. It was only two boards, and Ron and I got together and came up with a heatsink arrangement for it. So it has less fin area than a normal Larcan, and so it took a bit of fiddling to get it so it will stay cool. Here's the overall bits. Power supply, 24 volts at about 20 amps, I think it's capable. 50 volts at 20 amps. Problem with this solution, I usually use two 24 volt supplies because it allows me an easy step to get down to 12 volts or 24 volts for relays, but with a bit of learning, I've been able to adapt to the 50 volt only option quite easily. There's a 24 volt regulator, which is the extra added bit. Most switching DC to DC converters won't take 50 volts in, so I came up with a series regulator, single BD139, that regulates down to the 24 volts. 50 volt supply relay. The flavour of the month is a MOSFET. Various people, including W6PQL, do a MOSFET switch for in there. It's still a semiconductor, and if it goes boom, it usually goes short circuit, and you don't have any control over it. So that's a horn relay rated at 30 amps, and I've never had one of those fail. That's the half Larcan, and you can see, am I going to get a glimmer out of this? No, I'm not. You can see by the heatsink here that it was quite wide space fins, and I put additional fins down the centre to get the area up and improve the heatsink. Low pass filter, mandatory at 6 metres, and again, the design is one that I've used over and over. Will handle 600 watts, no trouble at all. So it should handle the 350, 400 that this is capable of. Reflectometer, and I'll describe that a little bit more later, but it's standard design, but in this case it's built with the printed circuit board out of a Larcan combiner. When you get a full kilowatt Larcan, it combines 2 amplifiers, and each of those amplifiers are combined versions of this half Larcan. They're usually combined with 3 dB combiners, and then the final combining is through some PDFE printed circuit board. So I cut that into strips and turn it into a reflectometer, and I'm getting repeatable results with that. Changeover relays, 6 metres, you don't need to use expensive relays. I know Ron's got a bucket full of them, but I still decided to go this way, Ron, and I put the big goodie in my 23 centimetre amp collection. There's standard on-rod 16 amp relays, and I'll show you again later on some references if you want to follow that up further. Our 6-inch fan, and it has got a speed controller on it, which is just a modified DC to DC converter. So instead of just having fixed resistors in there, it has got a positive temperature coefficient thermistor that is buried in the heatsink, and that varies the speed of the fan. So it's nice and quiet when it's normal, and if necessary it just keeps cranking the fan speed up. Now looking the other way, we've got the main switch. When you're selecting a main switch for this sort of equipment, it's got to handle the surge currents into that switching power supply. And they're pretty hard. You really want a 20 amp switch if you can get it. It's a 2-pole switch. One pole controls the mains and the other switches the 24 volts on and off. Reason for doing that is that's the reset for the microprocessor should it trip on an alarm. Just switch the switch on and off. The mains power supply won't discharge, but it'll reset the processor and allow you to proceed. Ammeter, the one Ron supplied, has got a shunt built in. I think it's 30 amps. So in this case, the amp only draws about 10. So rescaling would have been nice, but it'll be more than functional. There's a standard $3 24 volt to 12 volt, standard 24 volt to 12 volt converter, eBay special in there, and that feeds the 12 volts to the changeover relays, the power supply relay, and to the microprocessor module. There's a drive detector. In this case, it's just built up on a piece of PCB mounted on the input of the half Larcan. It's basically a shunt diode detector, and it provides the voltage to the microprocessor to tell us what the drive levels are. The controller, little nano, couple of transistors on the output of it, and 4 analog inputs which measure each of the parameters plus the press to torque. Dual needle SWR meter, and on the back of that there are 2 pots allow you to calibrate that meter. This one's set up for 500 watts full scale. So the level going to the controller's 5 volt max, and the dual needle SWR meter is calibrated to suit that for full scale deflection. And of course, they're all different, and I happened to pick up the printed circuit board for the controller that wasn't the 2018 model, it was the 2017 model. So the connectors are all different, and so this one I've supplied a spare programmed in case somebody finds the controller doesn't do the right thing somewhere down the track, and you're just a matter of changing the processor over. Power supply, straightforward. Mains filter, I think this was a mains filter out of a microwave oven. 50 volt supply, I said 20 amps. Circuit shows 12.5, which is more than enough. The amp draws about 10 amps. Power supply relay switches that through to the internal shunt ammeter, and normally I have a voltmeter in there as well on the 50 volts as it goes into the PA. I have put power supply overload protection on some. I don't think it's worth the effort, but there are two ways of doing it. One, you can monitor the voltage, the 50 volt supply, and if it pulls the power supply into current limit, the voltage will drop, and that'll give you an indication. Or there is some Hall effect devices which you can also feed into the micro. But by the time you get that indication, the FET's most likely disappeared anyhow. The second part of the switch goes through to the 50 volts to the DC-DC converter, and so that you can switch it off and switch it back on, and the 12 volt supply to the controller disappears instantaneously and resets that. The actual RF and control block, I'm starting to miss my pointer now. Here's the Larcan core itself, and it's got a reflectometer and a low pass filter. In fact, they should be the other way around, as they are in that example. Input power comes in through the aerial changeover relay and back out. Some of the amplifiers built to this recipe have a bias T to feed volts to a low noise preamp. And in that case, there is a separate relay that feeds 12 volts current limited out to the bias T. We've decided that we're going to put a 10 dB or a 20 dB attenuator in there if we're going to drive this from 100 watts. Most 100 watts radios will spike on initial press to torque, and that can damage the FET on overdrive. The drive detector just is not fast enough, and the micro are not fast enough to protect that. Only sure way is to put that attenuator in. Then the Nano itself looks at RF power in the drive. It looks at the power out, both forward and reflected. It looks at the temperature through a NTC and controls the power supply relay and the aerial changeover relays. Any questions on the core of the recipe?
How much, can you lose much dB through the relays?
No, 0.3. I looked at see if I had a results curve I could have put in today to convince people to use the two low-cost relays, but I found figures that show 0.3 of a dB loss. SWR about 30 dB.
And with the temperature coefficient, what's that?
10K beta of 3,750. But the nano can be calibrated for various things.
George, when you mentioned the low-pass filter, I understand why you have a low-pass filter on the output of an amplifier, but you said it was mandatory at 6 metres, as if...
You get up in frequency, like most of the microwave bands, or even 23. It's difficult to do a low-pass filter at 23, but the problem is 5G's coming, and the harmonics of...
I was going to say, maybe, I was thinking it, so you're saying it's that high that no one cares about it.
Well, not that. By the time it gets out through your coax and your aerial, you take the attenuation in coax at 23 centimetres, and you take that up to the second and third harmonic. There's not much coming out the end. And then you feed it into a narrowband Yagi. It's not working very well as a radiator either. So if you go searching for a 23 centimetre low pass filter, you won't find many people using it. And then once you get to waveguide frequencies and whatever, waveguide's going to do the job anyhow. This is a schematic of the half Larcan. The device is a Larcan branded device, but it is really an MRF 151, which is commonly used in 6 metre amplifiers. It has got input matching, make sure I get it the right way around. Input matching here. This ferrite provides a balun to feed from the unbalanced 50 ohm in to the push-pull input of the amp. These loops and the capacitors across them provide the input matching, as does this length and a capacitor across here if it's fitted. The bias is fed off that line there, which is 24 volts, and it goes through. There's a pot on this side and on that side to adjust the standing bias to 300 milliamps. The 50 volts is fed in via the fuses and then via these components here to provide a high pass filter into the output. The output matching is again the printed circuit board straps with the capacitors, output cupping capacitors, and then again a balun in this case is formed by a piece of coax which is grounded at this end and floating on both ends. This piece of coax, this piece of printed circuit board provides half the operation of that output balun. It balances up the ground effects of the coax cable. All right, the low pass filter. 3 inductors and then ATC type capacitors because of the power and the currents that are involved. They've got to be solid. I've had compressed mic capacitors fail, so I don't use those anymore. The circuit's quite straightforward. Capacitor input, it's an M-derived filter. Basically the two values on the input are half the value of the ones around the centered leg, and this is trapped so that it absorbs the second harmonic or rejects the second harmonic in passing through. That's the transmission curve. 0.3 of a dB loss in here as well, right at 50 megs, and a rejection of nearly 80 dB on the second harmonic. And that's nearly as good as they come. Third harmonic is better than 60 dB. And the SWR better than 30, which is better than 1.1 to 1. Here's the reflectometer. It's cut from a piece of Larcan scrap, which is PTFE board, 1.2 mil thick, and I cut the tracks down through this area to bring those closer or wider apart, depending on what sensitivity I want. The length of this section has got to be less than 1/10 of a wavelength at the operating frequency for it to work as a reflectometer. If you get standing waves along those lengths, of course the reflectometer goes missing. So then I solder the cut-off bits, and you can see the cut here and there, and solder that onto a piece of copper shim, fold the edge over and solder it down. Does two things: it provides a good ground and provides places to ground the matching resistors and the coax cables. And then the components, it's just a series detector diode feeding a 1 nanofarad 4K7 out to a 0.1. These strips are 1/8 inch wide, so they are basically 50 ohms. Here's the 50 ohm through section and the 50 ohm forward and reflected section, so it's terminated in 50 ohms. At opposite ends to give us our 2C. Our low cost aerial changeover relay, this one's based on an Omron G2RL, but there are a number of relays which you can quite quickly pick up on the web that will do the job. This is the printed circuit board I made for this one because I couldn't find the artwork for the earlier one as normal. They're all 0.3 of an inch wide tracks. Try again, 0.1 of an inch. I actually put that there, didn't I? They're 0.1 of an inch, 3 millimeters. That's where the problem occurred. So they're 50 ohms as well. So we come input into to the moving arm of the relay, a 50 ohm cross connect into the output and through 50 ohms to the output. And that again at 6 meters is better than 1.1 to 1 SWR. PA3 CSG has an article on low cost antenna changeover relays, and of course W6PQL has one, and they're slightly different, use different relays, but they provide reference material if you want to do one yourself. The processor, Arduino Nano, a couple of BD139s as outputs, transistors with diodes over them to allow you to drive multiple aerial changeover relays that may have different supply voltages, and to drive the power supply relay. Inputs go into analog inputs, and we have temperature, press to torque, forward power, reflected power. The front panel displays fault LEDs and operating LEDs. Power on is obvious. Press to torque comes on when the press to torque is received and the equipment's operating normally. If a fault occurs, that will go out and the fault LED will come on. And then there are 3 LEDs to indicate the source of that fault. The temperature LED will in fact flash if the temperature goes above ambient. It'll flash slowly initially and then come up to go on steady, and when it does that it'll trip the fault LED. So at switch on, it traps a press to torque that might be applied and warns the operator to lift the press to torque to allow the amplifier to start. It test flashes the LEDs on startup to show that everything's normal and that the LEDs are operating correctly. It operates the press to torque and aerial changeover relays on press to torque. It also clicks them briefly as an indicator to the operator that the circuitry is functioning on startup. It provides sequencing. One thing that is important in a high power amplifier is that the aerial is connected to the amp before the power supply is turned on, and on a fault or on release of press to torque, that in the opposite order the power supply is released and the aerial changeover is then released. If there's an LNA fitted with a bias T inside the amplifier, the LNA will be switched off, will not be switched on until the changeover relay is changed, so that you can't get transmit power into the LNA. It monitors drive, power output, SWR and temp. It'll shut down the power amp on fault, and it's sequenced as per that description. Cover those points. It also has the press to torque watchdog timer that shuts down the amplifier after 2 minutes nominal. Can be changed if you're doing something, but 2 minutes certainly covers all the digital modes. And 2 minutes is good, yeah. And there is a serial port, a USB port on the micro, and you can plug in there with a PC and it will read out all the analog values that are coming from the PA, and also give you an indication of the state of the outputs. So that's used for debugging the software in part, but also when you're setting up the amplifier and you're setting the sensitivity of the input drive detector and the SWR, it's useful to have those things presented to you as the micro sees them. No great secrets in this. This is a schematic of the controller. All the secret stuff is inside the nano. So we have the two outputs, one for the power supply and one for the changeover relays. By combining them with these diodes, this changeover relay can be 50 volts and that one can be 24 volts or whatever. So that allows you to have different voltage changeover relays. Temperature comes in from the PTC through a series divider into an analog input. The press to torque is pulled up to 12 volts. So when the press to torque goes low, again the analog input changes to low, and that is detected and debounced by the micro to give you press to torque. Power input, the reflected voltage, the forward voltage, and where there are multiple Larcans involved, for example, there is an auxiliary input which can be used to sense the balance, and if one amplifier fails, it can be used as a fault indication as well. 12 volts into the nano, and it uses its internal regulators to provide 5 volts to its internal circuits. These diodes along here are caught to the 5 volt supply, so regardless of what happens out here on the analog inputs, the voltage at the input to the nano analog inputs can never go over 5 volts. The previous amp built to this recipe was a 70 centimeter SPA NEC board worth about 150 watts, 24 volt supply. and the Nano. This is a input detector that I use not only for drive detection, but I use ALC on all my radios, and it can be used for, it has two detectors, one to drive the drive input on the micro, and another one to drive the ALC. This is a low pass filter for the 70 centimetres. You see, components are quite different to the 6 metre, and then a little SWR meter. And in this case, the meter calibrations are in fact fitted on the reflectometer. Okay. Thanks, Ron, for the hard yakka. You got most holes in the right place. And they didn't look like the hand shook too much at all.
Oh, he didn't have a drill press at the time, George. They were all done by hand.
It worked out very well.
And a bottle of rum.
I'm not commenting on that. Any questions?
Why did you use an analog input for the PTT?
Because it's there.
So, yeah,
It's there, all
that's what
right?
you had available.
Well, it's there, and that's what I had available. But it's quite easy to compare an analog value with a fixed value and then de-bounce that the same as you would a digital input. So it still has 40 or 50 milliseconds of multiple stage de-bounce to make sure it's right. And it works reliable, and it's in the recipe.
And what's the significance of PTFE as a material for the...
High power handling.
Right.
Because that's the combiner for the 1 kilowatt amp, and I use it in that combiner material. I use it in the reflectometer, and I use it as the base material for low pass filters at high power. You can use the FR4 board quite easily for 6 and 2 metres at M432. It's double-sided board, and the pads where the coils mount are in fact capacitors through the board. So that sort of gives you a part of the capacitor that's required, and then the additional values are put across it. And the only failure I've had with this design is you've got to watch the ratio of inductor to capacitance, or the inductors can get quite dark around the ears. Yes.
With the board there, you had the push pull coming into it, and you had the 50 volts through to fuses. So when you get to that part of the circuit, if you were to drop one of those fuses, how would the device handle that?
Well, it wouldn't very well.
No.
There's two aspects of that. The power would go down, and the balun wouldn't work particularly well. They're the two fuses, and they're primarily there to allow you to open a circuit and measure the quiescent current when you're setting it up.
So I'm not operating.
They're there, and I've never seen a failure there. And the way this is set up, if this device goes short on one half, which it could on a high SWR, then the power supply hasn't got enough to blow the bloody fuse anyhow. So that's why one of the reasons you may put power supply overload detection on it. But by then you'll know something has gone wrong. There is detection of output power against input power, for example. So if there's no output power and you're driving it, everybody out.
George, what I really like in using one of your amps is the bloody control. You know, you get a fault, bit of temperature, boom,
Yeah.
Gone.
The only time I've killed FETs with this controller is when I've been setting the bloody things up.
Yeah.
Because until you get everything right, and of course I have a dummy load which I can change the the reflective coefficient of to allow me to test the SWR, or I run 250 ohms off a T, and that allows me to set it up. But while you're doing that, it is really a little bit of nervous time, and I killed 2 FETs on this from our collection, Ron, or Mick, or who. I think I admitted that up front, didn't I, Mick?
No, not couple. At least more than half a dozen.
I have over the time,
Yes.
but only on this one I blew 2.
But
Which doesn't mean leave many left in the collection. One of the things to watch if you're following the recipe is the main switch is hard. The power supply is hard on the main switch. I have never had to put additional surge protection in the amp. A negative temperature coefficient surge protection in that could help, but I just pick a switch that's going to be reliable.
It has a warm-up time. What's the usual normal warm-up time before the thing starts to work?
2 seconds. Put the dummy load on it, all right? Now the dummy load's on it. Job's done, all right? Do you hear the relay say, I'm here? All right, okay. So if you drive this with a 100-watt radio, you got a fair chance you damage it.
Yeah.
So that's why we put the pad in there.
One of the things you brought up was that with the processor there, you said it was a serial input.
There's a serial port, a USB. So if you have a USB, or you've got a computer that it'll talk USB to USB serial, or you talk USB to RS232, and then just look at it with a terminal program, or an Arduino development system. It'll allow you to.
George, what protection do you have from the 240 in the system? Just the 240 fusing?
Well, you've got a low pass, you've got a filter board, and this filter board has got input capacitors and an MOV across the input, across the mains input. And then this power supply has all these Chinese specials. They're quite nicely done. Have got a low pass filter built into them with MOVs and capacitors. So it's pretty deadly sort of spike. And they're a switching type supply, so they'll run from 150 to 300 volts AC. They just don't care.
But if you manage somehow or other through stupidity to get a short circuit onto your 240, what happens?
The smoke comes out. There's a fuse on the back panel. 10 amp fuse on this,
You
yeah.
haven't really had a lot of that.
No, it's very rare, and if this does have a meltdown, the power supply has a meltdown. It's got an internal fuse, which will most likely go first. And most of the failures in here are due to the normal switching stresses that are on the switching transistors or on the detector diode, the rectifier diodes. No, they're very reliable.
So for our field days, the generator would be the key thing to make sure that...
Yeah, no, the generator, it'll handle the generator. It'll handle a brownout. If the generator goes low on volts, it'll follow it down till the voltage is 150, and then it'll shut down.
And how much rain can it take?
Rain, I don't know. I'm not responsible for that because it's mixed case. I think it's pretty good actually. It's got an overlapping at the back, and it's got a half-inch flange at the sides, and a bit of a flange. Oh, that's right. I put a 20mm flange at the front, so I think it is.
So no dew sensor?
No dew sensor. And the water run down the sides. One thing I do like about Ron's approach here, there's a lot of room, but I don't think there's a hole to let the water out. So that.
Yeah, that's good. The vent, it's got to get up.
It's got to get up to the vent, and by then there's trouble. No, a couple of holes. Oh, it's got a couple of 3mm holes in the bottom to let the water out. So.
Well, anyway, George, on behalf of the group here, thank you very much for coming in and making that available to us.
That's okay.
I think we ought to say a bit of a clap.
Thank you very much.